It gives me great pleasure to introduce my colleague, John Conway. He really needs no introduction, but you'll get it anyway. It's a short one, though. Conway has had a tremendous impact on modern mathematics. He's made many fundamental contributions in a wide spectrum of areas across the field, and I just mentioned a few of them here in group theory, in logic, number theory, combinatorics, geometry, etc., etc. He has made all kinds of very original discoveries, which have been influential in all kinds of fields, even outside of mathematics. I just call your attention maybe to the game of life and surreal numbers. These are really fantastic new ideas. And in addition to all this, Conway is a really remarkable expositor, writer, both as a writer and as a lecturer. I'm just reading his latest book, which I recommend to you very much, which is on symmetry. And Conway also has a tremendous range of admirers and enthusiasts, and among them was the late Giancarlo Rota, who wrote very positively about John, and I just want to quote a short review of a book by Conway and Sloan called Sphere Packings, Lattices, and Groups, just to give you a flavor of the kind of enthusiasm he elicits. This is the best survey of the best work in one of the best fields of combinatorics, written by the best people. It will make the best reading by the best students interested in the best mathematics that is now going on. So there is typical Conway. I think I'll conclude now just by saying that Conway's lectures are always stimulating, a lot of fun, and we're all in for a big treat. Oh, the mic. Just a second. I've got it pinned into the machine. Take this off. Oh, here. There.
Yeah. Well, high up this point. Okay, well, it's rather frightening to have to live up to that billing. But, well, it was rather frightening before anyway, and I'll just try to forget what Joe said. Yes. Well, what am I trying to say? It's one of the surest signs of senility in a scientist is when, or a mathematician for that matter, is when, after having made a reputation in one place, he somehow feels he can make a contribution to something else. And the diagnosis is clinched when the patient or subject, or whatever you want to call him, persists in this belief, even after having been informed that it's one of the surest signs of senility. By the way, let me say something. I said that because I didn't wish to impute senility to my colleague, Simon Koshin, over there. Everything about this theorem is joint work. I'm presenting it. Simon has done a lot of work preparing it, which we did together to some extent. The theorem itself emerged after discussions that lasted for years. And we weren't trying to prove this theorem. We didn't know what we were doing. We were just trying to understand what happens in the world at the small scale. And so anyway, By the way, Simon is a few years older than I am. So, you know, if I'm senile, maybe, well, anyway. Okay. But I don't want to, you know, if I say I all the time, I've been trying to practice saying we. It's not going to work, but I really am going to try every now and then saying we, because everything that I'm going to discuss was discovered jointly. And we had sort of complementary abilities. Simon has already made, 40 years ago, a significant contribution, which I'm going to tell you about in the next lecture of this series, to quantum mechanics, I mean to the foundational quantum mechanics. I never did. I took quantum mechanics courses in Cambridge, England, and I'm always boasting about something or other. One thing I want to boast about is that one of those courses was delivered by Dirac, famous physicist. However, I never understood much of what was going on, and I passed the exam, but only just, and after that I never sort of thought about it again until I met Simon. You know, there's this saying due to Feynman. Well, let me say it in the form in which I actually heard it from when Feynman was in a room. If you meet somebody who tells you he understands quantum mechanics, what have you learned? And he sort of asked various young people around him. Nobody sort of quite knew. He said, what you've learned is that you've met a liar. I've not met anybody who convinces me that they've understood quantum mechanics, although I have met a few liars in my time. Okay. Now, what this lecture is going to be about, this is also unusual for me. I'm very frightened of giving this lecture. What it's going to be about for the first part is a sort of survey of different philosophers' attitudes to the question of free will. It's been a question around, you know, for a long, long time, more than 2,000 years easily. This survey is not systematic or anything. The main reason for including someone is that we either agree with that person or disagree with that person. Okay, well, I suppose I get started, do I? Is there anything I've forgotten to say? I don't know. Yeah. Okay, so I might as well get started. Okay, yes. Well, thanks, Avi, for this. Yeah. What do I do to get the other one in? Come on. Ooh. Oh. What have I done wrong? Avi, what do I do now to get... Just wait. Avi?
Oh, with the right and left arrow.
Right and left arrow.
Right to go forward, left.
No, it's not to get to the next thing. It's to make this second thing fly up.
The other arrow, sir.
This?
Yeah, keep going with that arrow.
Okay. Okay. That's really the sort of problem that faces us. You know, I've given this audience, this sort of type of lecture to a number of audiences in a number of places, and customarily I've asked, you know, in the audience, you know, are there any determinists present? I know there are, because, you know, I talk in academic places, and how can I say it? The determinists are in general better educated than the free will thing, because free will is the obvious thing to think, you know, and determinism is a bit more subtle. I'm going to sort of argue in favor of free will, in a certain sense, but I know that free will cannot be, I'm saying I know. We know, we meaning Simon and I, know that determinism cannot be disproved. That's a very easy argument. And so let me tell you what it is. You go and see a really very interesting movie one day, and you don't know how it's going to turn out, and it's exciting. And next day you take a friend to see the same movie. Well, in a way, for you, it's determinist. But for your friend, well, it's not, it's free. Now, that's not the argument I'm talking about. That's just to give you an idea of what the argument really is. The argument is what we call the second time around argument. What's to say that we aren't at the second, as it were, performance of the universe movie? And we are being fed exactly, something went wrong maybe with the initial universe, and it's been started again. And we're being fed exactly the same sense impressions as we were first time around. Okay? In that case, if first time around was free, even if it was free, second time around is certainly determinist. Now, what does determinism mean? When I use it, it's going to mean a very precisely defined thing. It's going to mean that, how can I say it? Well, I'm going to, let me phrase the free will theorem that Simon and I proved. It says that if we, human beings, do indeed have free will, I'll define what free will means in a moment, then so do elementary particles have their own very small quantity of free will. And what does it mean? Well, I'm just using this term free will, and many people have said it's a tendentious use of words to mean that our behavior is not a function of the past. Suppose our behavior is entirely a function of the past, then whatever we do is, so to speak, what was written down, in a sense, in the big book before the world started. And what the theorem asserts is that if we humans, specifically some experimenters, have free will, in the sense that what they do is not a function of the past, in that very precise sense, then so do elementary particles. You might think it's obvious because we're made of elementary particles or something. I don't need that. So do elementary particles, even the ones outside us, have free will too, in that precise sense that what they do is not a function of the past. Right. When am I going to turn on this slideshow? I don't quite know. What was I going to say? This came as a big surprise to us. Actually, it's one of the things I most admire about Simon Koshin, my co-author, that, on one day in August 2006, we'd been talking about this thing for years. Every morning we talk about it for an hour or so, just trying to understand what goes on. Suddenly, the scales fell away that had been obscuring the theorem. And I turned to Simon and said, you know what we've proved? We've proved that if we have free will, so do the particles. He sort of went quiet for a bit. And then he said yes, and then he said, this means that my stuff with Axe is all nonsense, doesn't it? And, I thought a bit and said, something like, I'm afraid it does, it seems to. Now, he'd been working with his colleague Jim Axe for 2 decades on a theory that is now contradicted by the free will theorem. Fantastic. You don't get people who just drop it in 5 or 10 minutes. It was wrong. and that's that. So I admire Simon tremendously. There's another point in telling that, by the way, which is to say, you know, how can I say it? We were talking about today about how much we'd contributed, you know. We both came to the conclusion neither of us could have done it without the other. Simon had some technical knowledge of quantum mechanics that I no longer had. I told you I passed the exam. I was happy to forget it after that. Not exactly happy. I read the Scientific American articles on the subject. And, you know, they didn't seem very enlightening. So Simon had a certain amount of technical knowledge. He's not a physicist. He's a mathematical logician. I complemented that by my lack of knowledge, rather surprisingly. It was really important not to be able to understand quantum mechanics in some senses. So anyway, we did it. Right. Well, now what I'm going to do now is just survey a few philosophers. And as I said, I'm really concerned to just take the ones with which we agree or disagree. It's not, you know, I reject any reproach that I'm not presenting a complete sort of survey. This man's very interesting, Lucretius, full name Titus Lucretius Carus. He was a Roman, but educated in Greece. And the astonishing thing is, he was an atomist. He was a follower of Epicurus. The original people who invented the atomic theory, or who discovered it, are Leucippus and Democritus. But this man's particularly interesting to people who are interested in free will. So look, he's describing, you can read it, and I'm not going to read what's on the board to you in general, because that's rather stultifying. So I hope you can all read it. But he says, he's discussing these atoms, which in some sense are falling under gravity. That's not so important. I think they're being influenced by some forces. But he says, at quite indeterminate times and places, they swerve. And he explicitly says that he says that because it allows for human free will. And if they never do, then what's the source of the free will? You know, possessed by living things throughout the earth. And, whoops, I jumped on. Oh. And then he says this. Now, this quotation was too long to really fit on the thing. So I'm going to read it, which will include some of those words there. If I can read it, let me come over here. He says, although many men are driven by an external force and often constrained involuntarily to advance or rush headlong, yet there is within the human breast something that can fight against it and resist it. Now, wait a moment. I'm missing a sentence, but then, so also in the atoms, you must recognize the same possibility. Besides weight and impact, there must be a third cause of movement, the source of this unborn power of ours, since we see that nothing can come out of nothing. And then he goes on to say that the fact that the mind itself has no internal necessity to determine its every act, this is due to the slight swerve of the atoms at no determinate time or place. I find it fantastic. I mean, you know, historians of science have this slang term, Whig history, to mean that we judge people by the extent to which they agree with us, you know, they agree with the winning theory. I find it absolutely fantastic that somebody 2,000 years ago could have suggested that atoms actually, in some sense, have free will. Most scientists, until fairly recently, are determinists. You know, I'm going to take some particular cases of this, but Descartes is a very interesting person because his kind of determinism is only partial. I call it disconnected determinism. What he believed is that the physical world outside us, and even our bodies, but not our minds, operate mechanically in some sense. We're robots. But the mind, he says, is different. Here he is, a nice picture of him. He believed in determinism of the material world, but here's a quotation, that the will is by its nature so free that it can never be constrained. Some later people have also been, by the way, this is normally called Descartes' dualism. You know, there are two things, there's mind, or spirit, and matter. And, you know, matter operates according to one set of laws, and mind or spirit according to another. Descartes sort of wasn't quite as disconnected as some other people. Some other people say, well, whatever it is, reconciling the apparent determinism of the universe with the apparent freedom of the mind is something to be postponed until later, when we understand it, you know. So they sort of have a provisional attitude, which is disconnected determinism. I'm going back now to have a little look at compatibilism. This is something that there are many varieties of compatibilism. It is, you know, it comes out, it sounds very strange at first to people who haven't lived in philosophy departments, roughly speaking. It says that there's nothing incompatible about determinism. We can, and free will. We can will freely to do something, and then whatever we will happens. Oh, God, I can't explain it. Let me see if I can find. Well, I find it so strange. I mean, a man. So look at that top sentence. A man was free in those. This is from a dispute between Hobbes and Bishop Bramhall, or Archbishop Bramhall, Archbishop of Armagh. A man was free in those things which were in his power to follow his will, but he was not free to will. The will was determinate, but then he was free. It sounds a bit funny, but in the, you know, it's not contradictory, although it looks it at first sight, I think, to many of you. To me, it looked contradictory in a way, but it's not contradictory at all. The second time around argument that I gave you can be sort of viewed as showing that this is not inconsistent. However, what am I going to say? Let me go back to Descartes' dualism. This is explicitly contradicted by our theorem. Okay? If people can choose which experiment to perform, then the particles outside us can choose what their responses are. That's our theorem. By the way, what do those words mean? Isn't it funny to speak of particles making choices? It seems to involve deliberation. I'm not pretending the particles are conscious or anything. We are not pretending the particles are conscious. But there are lots of different words we could use. For instance, free will, I mean, lots of philosophical discussions about free will are concerned with the question of assigning moral responsibility. You know, if I'm a determinist, or if the judge is a determinist, I might argue, you know, it was all determined, I just had to do it. I'm not responsible for my actions. I'm not concerned, we're not concerned, with assigning moral responsibility at all. I want you to think of what we're discussing, if you like, as free whim. Namely, look, here's this book, I finished reading it now. What am I going to do with it? I decided to drop it. Now, I don't think that was forced by the history of the universe. You know, I really don't. You know, I can't disprove you if you think it was forced. We've already shown that. I'm not going to argue with convinced determinists. There's no way of winning. But I believe, and most people believe, until they get educated out of this belief, that we are in fact free. I'm going to present arguments, but only in the last lecture, and they're not deductive arguments, to strongly support the idea that we do in fact have free will, but not to prove it at the deductive level. Let me continue a little bit. Right. Here's another guy. Oh, by the way, why is Hobbes there? Well, because this notion of compatibilism has been around. It's been long before Hobbes, but Hobbes stated it very clearly, his own particular version of it, in this discussion with Archbishop Bramhall. Neither man wanted the discussion to be published, by the way, but it was eventually. So it somehow got associated with his name. He popularized this notion of compatibilism in a way. Right. Here's Leibniz, a great philosopher. And he has this principle of sufficient reason, which says, well, you see it, that nothing happens without a reason why it should be so rather than otherwise. He states this principle countless times in, well, this is a book of selections from Leibniz, which I used to put myself to sleep with. It's very repetitive. He's got all sorts of arguments and so on. One consequence of the free will theorem, not quite a consequence, it's a consequence of the free will theorem plus the assumption we actually have free will, is that even in the inanimate world of particles, it's not true, this principle of sufficient reason. A particle does one thing or another, and there's no reason to be assigned. There's nothing in the previous history of the universe which tells it what to do. It does one, or it does the other. Okay, now here is Laplace, the Marquis de Laplace, who wrote this huge book, Mécanique Céleste, discussing the motion of the planets. Now, one reason I think why determinacy got its a really big impetus from the development of science was that Newton's theory of gravitation and so on, as I explained, was entirely deterministic. It left no room for freedom. And the Marquis de Laplace, who did a lot of work on Newtonian gravitational theory, says that, an intellect, somewhere else it's been translated as an intelligence, which knew where all the particles were at some moment and how fast they were moving and so on, that every single thing could be known to that intelligence, provided a pretty good calculator. It could reason out exactly what was going to happen in the future. Laplace makes this statement in several different places, and it's the strongest, I think, assertion of determinism in the scientific literature. I don't believe it for one moment. And I think it's just a consequence. The rise of determinism is just a consequence of the fact science advanced tremendously as a result mostly of the work of Newton and people like Laplace. They could determine things. But it's only the large-scale science that, in fact, seems to be deterministic. This century, it's not been so. And I think there are a lot of people who sort of believe that, somebody said, what is it? We have to, we have to believe in free will. There is no choice. That's a nice, a nice sort of paradox. There's a guy called Dennis Overby who writes about science in the New York Times, and he's several times published articles in which he says everything we know of science convinces me, that the world is deterministic. Nevertheless, I cling to the illusion of free will. I'm not quoting his exact words. Somehow I can't run my life without this illusion. Some people have described it as a necessary illusion. We don't think it's an illusion. It's not an illusion. We think we have free will. And on the other hand, the arguments that suggest we have free will can't be turned into logical deductive proofs. There's nothing wrong with that. If you argue in a court of law, you saw Mr. X going up the staircase to Mr. Y's apartment carrying a knife, and he'd been heard to utter threats before, and then Mr. Y's body is found, and the knife seems to be the knife, and so on. We sort of conclude, although we haven't got a proof, that probably the culprit was Mr. X. We can give reasoning of that type, but stronger. I mean, there isn't in the end any kind of reasoning that's called inductive reasoning, or part of it is called inductive reasoning. There isn't anything really in the last resort that isn't inductive. Even the laws of deductive logic have been established only by induction. Of course, the inductions there are many, many, many supporting instances. But, okay, so I'm trying to say it isn't a complaint that we're using. I mean, I don't think it's a legitimate cause of complaint that we use inductive logic only. We can't use deductive logic. I've already shown you that, It doesn't mean, however, the consistency of determinism doesn't mean that it's true. Mathematicians are accustomed to have consistency proofs. They say nothing about truth. They just say something about what might be true. This is interesting because this is a recent philosopher. Unfortunately, he died quite recently. SR is Leibniz's principle of sufficient reason. And he then goes on to say, moreover, theorems show that any theory that retains certain features of quantum mechanics also won't satisfy SR. And you see there's a reference to the Cauchy-Specker paper. This is a paper 40 years old, roughly, more than 40 years old, in which Cauchy, my co-author, and Ernst Specker, another logician, they're both logicians, not physicists, that might seem to disqualify them from saying anything, approved this Cauchy-Specker paper. From my point of view, from our point of view, this is not enough. The Cauchy-Specker theorem is not as strong as the new theorem. Okay, so let me say roughly what happens. Okay, well, there's a statement of the free will theorem. If indeed humans have free will, now I only mean this in a very restricted sense. I don't suppose much free will. Namely, I mean, the supposition is only that the human can choose which one of 33 buttons he wants to press. And then he presses that button, and after that, that button's pressed. What I'm trying to say is this choice affects the future history of the world in a minor way. We know that that button was pressed after it was pressed. Before it was pressed, we didn't know which one it was, and I believe that a human experimenter has that much free will. That's the only amount of free will, I suppose. We suppose nothing about these deep questions of moral responsibility and so on. In trying to make a theory scientific, you remove the additional distractions. You have a knob that just controls one parameter at a time, and so on. Because otherwise, if all the parameters move, you don't know which was it that caused the effect that you're studying. Well, here we're not tying this with any moral responsibility. It doesn't matter which button you press. Nobody's going to die as a consequence of your pressing one button rather than another. It's not mixed up with these things. Okay, and so, well, let me perhaps explain the axioms a little bit later. Right, so here's what they are. There are 5 more things. The first one is going to be about this Cauchy-Specker paradox. And I think rather than describing what this paradox is now, I'll say what it does. So there's a thing called measuring. Well, there's a problem in physics, the measurement problem. And the thing is, it's been called the measurement problem. That's a wrong description. There's a thing that's been called measuring the squared spin of a spin 1 particle. Don't worry about all that technical stuff. Let's say measuring the spin, of measuring the component of spin, I'm sorry, of a spin 1 particle in a certain direction, the squared component of spin. I'm going to leave all those words out after a time. Here's a particle, and I sort of direct my finger at it, so to speak, and ask it, what's its spin in that direction? And it doesn't matter what spin is. It's vaguely like imagining spinning, but it's not really like that at all. It's a very subtle concept. But anyway, the thing is, this particle is quantized. In the nature of things, it can only give 2 answers to this question, 1 and 0. If I hadn't put that word squared in, it could give 3 answers, 1, -1, and 0. But squaring identifies 1 and -1. So it can give 3 answers to this question. Now, initially, it was the obvious thing to do to believe that this concept existed before you measured it. But that was found not to be so. What the Cauchy-Specker theorem says is that it can't exist before you measure it. And the reason it can't exist is because there's no consistent set of answers to every question. When I was a little boy, I had 2 sisters, 5 and 10 years older than I was, and we used to play 20 questions. And I think I was a rather bumptious little boy. And certainly I had no moral sense whatsoever when playing 20 questions. You know the thing, you choose an object, you say it's animal, vegetable, or mineral, and then your sisters ask you questions about it. If they succeed in getting the answer in 20 questions, you've lost. Okay. Well, if I thought that my sisters were getting near to my object, I changed what the object was. Okay. Now, you have to be quite clever to do that. I was quite clever. They caught me out every now and then. Because you have to select a new object which answers, say, the 7 questions you've already been asked in the same way as the old object did, And on the other hand, is also unlikely to be the kind of object your sisters will think about. Okay. That's what the particles do. They, if you ask them this type of spin question, they don't have an object in mind. Let's think of that. Let's think of an even cleverer little boy than I was. Very hard to think of a cleverer little boy than I was. But think of a cleverer little boy than I was who never bothers to select an object in the first place. Just gives, the first so many answers at random and then starts thinking what the object is. Well, that's what the particles do. They don't have answers in mind for each direction you can have. You might wonder how it can possibly be proved. Well, Cauchy and Specker proved that a long time ago. And the reason, ultimately, is that there's a little puzzle to be solved, and that puzzle has no solution. In fact, they used 117 directions, but this man Asher Paris, another person who's unfortunately died fairly recently, reduced this set of directions to 33. So we have 33 particular directions, and there's no conceivable set of answers to that that's consistent with what we call the spin law. Maybe I'll have to tell you what the spin law is, but I think I won't do it just yet. What time is it? Okay. Now, okay, a clever enough little boy can answer questions like that on the fly, so to speak, and not be caught out by his sisters. I may say I was often caught out by my sisters, and there were sort of punishments which I won't bother to describe. But suppose I had a twin brother. In fact, there was a long history of twins in our family. My father was a twin. He had a brother and sister who were twins, and so on. I always wished I had a twin brother. And if I had, my sisters would have had a much better chance, because, you know, they could sort of allow us to choose our object together, but then interrogate us separately. And then we can't change the object. You know, if they choose which one they're going to ask the object to, without transmitting information saying, oh, I'm changing the object to such and such, we couldn't win. And that's what manages to happen in the particle case. This is the additional thing, which, by the way, Simon also thought of a long time ago, but he didn't sort of put together the thing to deduce the free will theorem. So what's the point? Well, you've probably heard of the theory of relativity. Some people distinguish, you know, they've even heard of the theory of general relativity. Most of us have heard the assertion that you can't transmit information faster than the speed of light. Most of us, I think, hear it on authority only. We don't really understand why not. Okay. And the reason why not is because of this funny property of relativity theory that there's no absolute notion of time. Time depends on which coordinate system you're using, on your frame of reference. And this is sort of quite astonishing. As seen from one frame of reference, event A can be before event B, and as seen from another frame of reference, event B came first. The world hasn't got a standard definition of time. When I say the world, I mean the universe, by the way, in here. And it's hard for us to understand how that can be the case. Well, I have a very simple way of explaining relativity theory with no formulae, don't worry about it. And I've tested it out, I think in this very room, before an audience like this 10 years ago. And if you follow that, you'll understand how it comes about that it's impossible to transmit information faster than the speed of light. The reason is, if you could, then seen from another person's point of view, you'd transmit information backward in time. So we would know the result of somebody's experiment before they performed it. And if they have free will, you can't do that because, you know, you'd know the result of their choice before they made it, and they're free to make another one. So relativity is an important part of the game. Okay. But then the funniest thing, I think, the strangest contribution of quantum mechanics to this discussion is the EPR paradox. Now, in, I think, 1935, the New York Times had an announcement that Professor Einstein was going at the next meeting of the American Physical Society to disprove quantum mechanics. Einstein was always suspicious of quantum mechanics, for good reason, I think, but anyway, he was wrong. He wrote rather furiously to the New York Times the very next day, insisting that they apologize. And it turns out that one of his two collaborators, the paradox is due to Einstein, Podolsky, and Rosen. It's called EPR. Had let the cat out of the bag, and Einstein didn't want it let out of the bag before the official announcement. That's quite a time ago, more than 70 years ago. Okay, that's an essential contribution to our theorem too. So what happens is this. Despite the fact that information can't be transmitted faster than the speed of light, remote events, remotely separated events, can be correlated. You can assert, and this is the content of our twin axiom, you can put two particles into a state which is called the singleton state, and then you can get them apart, and it's got a rather curious property. This spin is an aspect of angular momentum. And when you put them into the singleton state, it means you verified that the angular momentum of the pair of particles is zero. And that, by the conservation of angular momentum, means that if you measure the angular momentum of this in any direction, then for the angular momentum of the other one, you get the negative answer. But remember, we're going to square it. That means our concept, which is squared component of spin, is the same. So let's say these particles have been sort of hypnotized. If you ask one of them a question and you ask another of them a question, they will give the same answer. This is like the situation I envisaged where I and my twin brother promised to give the same answer to questions. And the funny thing is, even though the Cauchy-Specker theorem proves that the answers do not exist ahead of time, the equality of the answers can exist. So, I mean, if I ask this question of this particle, and I ask the same, or my colleague on Mars asks the same question of the other particle, then even though those questions aren't determined, the answer to them ahead of time, they don't exist ahead of time, the answers, by the Cauchy-Specker paradox, they'll give the same answer. Now, of course, I don't know that my colleague has asked this question, the same question as I do. He may not have done so yet. In fact, it's meaningless to compare the times at which we do it, because time is not an invariant concept. But, so I can say, if my colleague on Mars has asked the same question, or if he will ask the same question, or if he's now asking the same question, whatever it is, he'll get the same answer. That is the EPR paradox, the fantastic thing that Einstein thought would disprove quantum mechanics. It is, in fact, perfectly consistent, but ever since it was discovered, people have been trying to explain it away, in some sense, because it's hard to believe. We can do this at times that differ by 1 microsecond, in which time light has no hope of getting it. Mars is always at least 5 minutes away from us. Okay, but nevertheless, the answers are going to be the same. Right. Now, I'm not going to sort of really describe the proof of the free will theorem. It's sort of plausible right from the start. It says, we consider this experiment, this twinned experiment. Let me go back and see what I have actually said about the axioms spin, fin, and twin. Twin is the thing I've just described. It is possible to put two particles, to have put two particles, should we say, even remotely separated particles, into a condition in which, if asked the same questions, they will give the same answers. If they're not asked the same questions, all bets are off. Okay. That's called twinning the particles. We call that twinning the particles. It's an instance of what's called, in the slang of physics, it's called entanglement. Fin is the axiom which comes to us from relativity theory that information can't travel faster than the speed of light. Well, let me now talk about spin. Spin is this rather curious axiom. If you take one of these particles and ask it what its squared component of spin is in 3 different mutually perpendicular directions, it always happens that 2 of the answers are 1 and 1 of them is 0. That's most mysterious. And in fact, it's not possible to solve this puzzle. You know, we have these 33 directions, and it's not possible to assign 0s and 1 to them subject to essentially that condition, which we call the 101 rule. So that doesn't stop the particle, which is acting in some ways rather like a little boy. It's making up its mind as it goes along. It doesn't stop it from giving answers, but it does stop the answers from being determined ahead of time. And that's the guts of it. Let me tell you that spin and twin are operationally definable, is the term. That is to say, okay, you don't believe me. I don't want you to believe me, just on authority. So you don't believe this 101 law, say. Well, come to my laboratory. Imagine, please, that I'm a physicist, a much more practical person than I actually am. Come to my laboratory where there's equipment for doing this set up. Measure the squared spin of a particle. Do the operation that's called measuring the squared spin of a particle in 3 different directions, 3 orthogonal directions. Do it 1,000 times. And you'll always get 101. Well, no, you won't. 999 times you will, and the other one's experimental error or something. Our theorem is actually robust. You don't have to measure at exactly 90 degrees. As long as you're close enough, that's good enough for the theorem. Again, you don't believe that these remotely separated particles always give the same answer. You know, these are consequences by the way of quantum mechanics. But, you know, you don't understand quantum mechanics. Nobody does. So you're entitled not to believe it. But these are not, we're not assuming quantum mechanics. We're just assuming these axioms, twin and spin, that follow from quantum mechanics. You don't believe the twin axiom. Well, again, do the thing called putting these 2 particles into the singleton state, where they're twinned. Measure them as many times as you like, ask them the same questions, and see that they always give the same answers. That's what it's meant by saying that those things are operationally definable or decidable. Now, Finn, the axiom that information can't travel faster than a finite speed, that's where it gets its name from, it does not have that nice property. I mean, some people, I think they're rather silly, believe that, say, ESP travels instantaneously, whatever it is. I can't disprove them. You know, I mean, I can't disprove that somehow there isn't an as yet undiscovered way of transmitting information faster than the speed of light. So that's not the evidence for Finn. That's why it's so important that I show you why that follows from a symmetry principle. That the laws of physics are independent of the coordinate frame you're using. If you're traveling with respect to me at half the speed of light, you still have the same physics. And it's that symmetry principle that's been tested in countless ways. And so that's really why we believe Finn. So what I'm saying is there's very, very strong evidence that these 3 axioms we use are true. Okay? Well, they may not be. You know, somebody may discover that beyond a certain distance, this twinning breaks down. Well, that would be an earth-shattering discovery in science. It would get a Nobel Prize straight away, you know, that's the sort of thing. The sensible thing to do is don't bet on that. You know, you should really believe in the things that have been tested very, very strongly until there's some evidence against them. They're continuing. So don't think that, I believe unreservedly in quantum mechanics. Well, I'm not going to change my mind before there's some reason to change my mind. Okay. Well, it says 9 o'clock here. Okay, so the last lecture is going to be about the consequences of our free will theorem. So I'm going to prove those things, or remind you again of what I've already, in a sense, done. Descartes' kind of disconnected determinism won't work. That's it. It's gone. Leibniz's principle of sufficient reason won't work. It's gone. Now, perhaps I should say something. Well, wait a moment. These are more detailed descriptions of the proof and so on. Perhaps I should say something about... I've forgotten what I was going to say. So perhaps I shouldn't say it. I shouldn't try to say it. This is enough. We've had an hour. Now, I want to sort of remark, I'm going to be here, and so is Simon Koshin, my friend. If you want to ask him a question, rather than me, if you want to see to what extent our opinions differ, we're going to be here from now on, from 7:30. That's to say, half an hour. We were today. Half an hour before the lecture starts. And then we're going to be here for half an hour after the lecture finishes as well. So you're very welcome to come along and ask questions. Oh, I know what I was going to say, and I bet I had say it. It's hard for me to say it, that physicists in general have seen lots of instances of people coming up without proper qualifications in physics and presenting some sort of loony theory, and they don't read them. We had this thing in mathematics once. People sort of thought they'd proved Fermat's last theorem was what happened there, and they never had. Eventually somebody did, but he was a very distinguished and high-powered mathematician. So what am I trying to say? I'm perfectly prepared for the fact, that physicists, especially the ones who don't read our paper, don't believe it. They think it's just another one of those strange things. However, it's rather better than that. And I hope, I see one physicist, at least in the... No, I see another. I hope that the physicists stay and learn something from us, even if, what they learn is wrong. There's one other thing I want to say. In many respects, this is not in any way an unorthodox opinion. You might think it is. But, physicists have lived with these paradoxes really for 80 years now. They have been accustomed to the fact that quantum mechanics is not a totally predictive theory. And they've proved long ago that no extension of quantum mechanics can be. This is not a defect of quantum mechanics, so to speak. It's not a temporary defect anyway. No extension of quantum mechanics can recover that total predictivity. From our point of view, that's sort of obvious. No correct theory can predict what a particle is going to do before it's made its decision what to do, while it's still free to do something else. Okay, so it's not to be seen as a defect in quantum mechanics that it doesn't predict. It's a merit. You shouldn't expect to be able to predict things. Nevertheless, when this non-predictivity of quantum mechanics was discovered, it came as a great surprise. People tried to explain it away. They tried to find larger theories. Many people invented larger theories. They're sort of, I think, fringe physicists, but many of them are respectable physicists. It's in no way, how can I say it? If you believe that there is some kind of extension and create one, nobody has succeeded in making one of these theories relativistically invariant. And physics appears to be relativistically invariant. So what am I trying to say? Physicists have believed in a certain sense in the result that we're proving for a long time. It's no surprise. I knew all that, they say. However, what they didn't know was that it can be deduced in this very precise logical fashion from so little information. And moreover, information that is not at all contentious. You know, these three axioms we use, they're routine, they're accepted. You know, they follow from quantum mechanics and relativity. There's nothing dubious about them at all. And that's all we need to sort of, you know, the original deductions that quantum mechanics was not a complete theory, those deductions used more. They used all sorts of properties of quantum mechanics. And some of them were sort of pretty poorly understood ones. And, okay, well, I'm repeating myself. I'll stop.